So just kind of as a recap, yesterday what we did was simplifying. Oh, I guess we're doing purple today. Simplifying. Multiplying. And dividing. So all of those were kind of the same process, right? Like we just factored everything in sight and then canceled common factors. If we're dividing, we have to write it as multiplication first, but then it's just that same process. So we factor the numerator and denominators. Then cancel common factors. So for example, like with numbers, we could do like 3 over, it's an ugly 3, 3 over, how about 80 times 12 over, say, 70, maybe. And so we'd factor, right? We'd do 3 times 2 times 2 times 3 over 2 times 2 times 2 times 2 times 5 times 7 times 2 times 5. This isn't very exciting because there's not much to cancel. So you can cancel like 2 2s. And we end up with 9 over, I changed colors, I didn't mean to do that. 9 over 140. No, 1400. Yep. So when it comes, well, you guys have calculators, you can plug that in. Somebody might want to check my 1400. I think it's 1400. So then the process that we use for adding and subtracting is going to be slightly different than what we did for multiplying and dividing. What do you need to add and subtract fractions?
Common denominator.
Yes, common denominators. So when we add, subtract, our initial goal is going to be to get common denominators. So let's use just those same fractions. If I wanted to add 3 over 80 to 12 over 70, initially, I might not know just by looking at that what my common denominator would be. And so if you can't tell just by looking at it, we can use prime factorization to find the LCM, just like we use prime factorization to find the GCF. So we could say 80 is equal to 2 times 2 times 2 times 2 times 5. And then 70 is equal to 7 times 2 times 5. And then to build an LCM from that, the idea of the LCM is that in order to be a multiple of a number, you have to contain all of the number's prime factors. So if I want to be a multiple of 80, I have to have 2, 2, 2, 2, and 5. And to be a multiple of 70, you have to have 7, 2, and 5. But we don't have to repeat things that they both have. So I always start my LCM just by copying one of my factorizations. So 2 times 2 times 2 times 5. And it doesn't matter which one you start with.
Don't you need another 2?
Oh, thank you. Bad copying. And then I look at 70 and I ask myself, are there any factors in the factorization of 70 that I don't already have in my LCM? Just a 7, right? And so we need another factor of 7. And that's going to be my LCM. And you can check that you have the factorization of each of your numbers in there independently, right? So there's my 80. And then there's my 70. And they don't have to all be next to each other. It worked out nicely in this case. But just somewhere in that factorization, you have to be able to find each of the prime factorizations for each of your numbers. And so this ends up being, I think, 560. So then to do that addition, I'm going to multiply each of my fractions by a factor of 1. Right? So this is an expression, which means that I'm not allowed to change its value. And so all I can do is multiply by 1 or add 0 is like really the only thing you can do that doesn't change the value of something. We have lots of creative ways to multiply by 1 and add 0. When we say multiply by 1 in this setting, we just mean multiply by a fraction that's the same on the top and the bottom. So we have 3 over 80. And we're going to multiply by 7 over 7 to get 560. And then if I have 12 over 70, I'm going to multiply by 8 over 8 to get 560. And so we end up with 21 over 560. Whoa. Plus 96 over 560. And notice that this is different than when we cleared fractions, right? Like when we cleared fractions, we multiplied by our LCM over 1. So if these equations were, or if these fractions were in equations, I would multiply both sides of the equation by 560 over 1 to cancel off all my denominators. But I can't do that here because multiplying by 560 over 1 makes an expression 560 times bigger. And if I don't have another side of the equation to balance out that change, like to also make 560 times bigger, all I've done is just made a different number, right? So, which defeats the purpose of simplifying something if you just turn it into something else, right? Why not just turn everything into the number 1 and simplifying's easy. So I have to maintain the value of my expression. Since I don't have an equation to keep balanced, I can't change the value at all. So I have to multiply by the same thing on the top and the bottom as opposed to the same thing on the left and right of an equation. So then when I add these, I get what, like 117 over 560. And my next step would be to simplify that, but I'll do it, but it can't be simplified. So this is 3 times 3 times 30, 9, 20. 9 goes into 11 once. 13, there we go. And then I know that the factorization of my denominator is 2 times 2 times 2 times 2 times 5 times 7, only because I have it over there, right? That's already factored over there. And we see we don't have any common factors, so this doesn't simplify. So we can just get rid of that. And that's fairly common when we do addition and subtraction to like get something kind of ugly and have it not simplify at all. So don't be alarmed if that happens when we do this with rational expressions too, like on your homework. If you can't factor the numerator, it doesn't mean you did something wrong. Like it happens all the time when we do addition and subtraction. So let's try doing this with polynomials. So we're going to follow the same exact process. We're going to factor our polynomials and we're going to build that LCM from their factorization. So let's find the LCM of, we'll do x squared plus 2x plus 1, 5x squared plus 5x, and then x to the 4th minus x squared. Okay, so just like we did yesterday, we're going to put each of these in parentheses to remind ourselves that we can't work separately with the individual terms. Like I can't factor the x squared as x times x, right? Because that's a term of the polynomial. I want to think of each polynomial as like a single number almost, right? So it's one thing and I have to factor it as a whole. So we have this guy, and this guy. So we're going to factor each one of those as a whole polynomial, and then we'll build our LCM from that. So we have x squared plus 2x plus 1, and that factors as x plus 1. Come on, buddy. Times x plus 1. And then 5x squared plus 5x. Well, I have a common factor of 5x. So we have 5x times x plus 1. And for your factorizations, again, like I'm just doing this in my head to save us time so we can focus on like how we're finding the LCM and not on factoring. But when you guys do these problems, when you have to factor, just like go to another part of the paper or another sheet of paper and do whatever work you have to factor your polynomials and then put it back into the problem. I'm not by any means saying that you have to do all this in your head at this point. So whatever it takes for you to factor them. And then my last one was x to the 4th minus x squared. This one kind of takes 2 steps, but it ends up being x squared times x plus 1 times x minus 1. Okay, so now I'm going to build my LCM. So just like I did in the last problem, I'm going to just start with the factorization of one of my polynomials. I always just start with the first one. It doesn't matter which one you start with, though. So we're going to start with x plus 1 times x plus 1. And then are there any factors in that second factorization that I don't already have in my LCM?
5x.
Yeah, 5 and an x, right? So 5 times x, and I already have an x plus 1, so I don't need another one. And then are there any factors in my third factorization that I don't already have in my LCM?
X squared and x minus 1.
So there's an x minus 1, but then with the x squared, remember that x squared is x times x. So do I need 2 factors of x? What do I need? I need 1 factor of x, right? Because x squared is x times x, and I already have a factor of x here. Remember that 5x is 5 times x, so it's a factor of 5 and a factor of x. If I already have an x, I need 1 more x to get x squared. Oops. So times x. So if I was going to put this together to make it look pretty, which you don't have to do, like this would be a perfectly acceptable answer, but this would be 5x squared, and then x plus 1 squared, and then x minus 1. So see how that 5x squared, it contains a factor of 5x, and it also contains a factor of x squared, right? So we don't need x and x squared separately. We want to remember that if something is squared, that it's just multiple factors of a single variable. And if you want to, when you factor, you can write it, when something's squared like that, you can write it as x times x, if that helps to see like those individual factors. Good? Okay, so let's do some addition, subtraction. So we're going to start, let's see, adding. subtracting. Need to leave room. So the first step when we add and subtract rational expressions, if my goal is to get a common denominator and I want to find the LCM, in order to do that, I'm going to have to factor all my denominators, right? Just like we did in the previous example, to find the LCM, we had to factor all the polynomials. And so we're going to start by factoring the denominators. This is a little bit different than what we did yesterday in that we're not factoring everything, we're just doing the denominators. The reason for that is that later on, we're going to add the numerators. And if we factored them, we'd have to distribute before we could add them together. And so we're just going to leave the numerators alone for now. We're going to focus only on the denominators to get common denominators, and then we'll worry about the numerators when we're ready to add them together. So we're going to factor all our denominators. So let's do an example as we go here. Let's see, how about this one looks good, 2x plus 1. Okay, so we're going to start with factoring. We're just going to put those numerators in parentheses, just like we did yesterday, just to group them. And then this guy, oh, I'm sorry. This needs to be a 2. I miscopied that, I apologize. Everybody got that? Sorry, my bad. Good, okay. So this factors into x plus 1 times x plus 2. And then the second one, I've got x minus 2. And then when we go to factor this 1 minus x squared, remember we want to put it in descending order. Factor out a negative 1 to get a positive first term. And then that factors as x plus 1 times x minus 1. So we have negative 1 times x plus 1 times x minus 1. But when I see that negative in the denominator, it totally freaks me out, because if I keep a negative in the denominator of one of my fractions, that means that to get common denominators, I'm going to have to multiply by a negative over a negative in every single other fraction, which sounds to me like a lot of negative signs to keep track of. Like, it can get crazy. So instead of doing that, I am going to just move the negative to the top. And we're allowed to do that because if you think about fractions, if you have like a negative fraction, like negative 3/4, you can get a negative number by dividing a negative by a positive, or by dividing a positive by a negative. So when you have a fraction, that negative sign can be anywhere in the fraction. So right now we have a negative sign in the denominator. I'm just going to put it in the numerator so that my LCM doesn't contain a negative. And we're allowed to do that because we're just saying we're dividing a negative by a positive instead of a positive by a negative. So we're going to take this guy and move him up. And the 1 really doesn't have, I mean, we can leave the 1, like we can just move the negative sign. But a factor of 1 doesn't do anything anyway, so it doesn't really matter if we take it with us or not. So now I'm ready to get common denominators. So I'm going to start with 2x plus 1 over x plus 1 times x plus 2. And the idea here is that I want all my denominators to be the same, which means they have to have exactly the same factors. So to me, the easiest way to think about it is like we're playing like the what's missing game, right? So anything that the one on the left has that the one on the right doesn't have, the one on the right wants. And anything the one on the right has that the one on the left doesn't have, the one on the left wants. So it's like if you give two kids like a handful of candy and one of them's like, he has 2 yellow ones and I only have 1. So you can't very well take a yellow one away from one of them, right? You have to just give another yellow one to the first one. And then the other one's like, oh, but he has 3 green ones and I only have 1 green one, so you have to give him 2 more green ones. So everybody wants the same amount of everything. So we're going to say what they have in common already is a factor of x plus 1. So everybody's got that. Nobody's upset. But the fraction on the right has a factor of x minus 1 in its denominator, which the one on the left doesn't have. And so we're going to multiply by x minus 1 over x minus 1. And then we've got our x minus 2, which is negative now, remember, because we moved that negative up. And we see that the fraction on the left has a factor of x plus 2 in the denominator that the fraction on the right doesn't have. And so we're going to multiply by x plus 2 over x plus 2. So our next step here was to get common denominators. I can see this becoming a big mess. Okay. Get common denominators. By multiplying each fraction by a factor of 1. So a fraction that is the same on the top and bottom. And then we can verify that we do in fact have common denominators just by checking that everybody has the same factors in the denominator and the same number of each factor. So they both have a single factor of x plus 1, they both have a single factor of x plus 2, and they both have a single factor of x minus 1. So I do, in fact, have common denominators now because everybody's got the same exact factors. So now we're ready to do our addition. So we're going to do one big fraction. And when we get common denominators, when we add them, we keep that same common denominator, right? So we're going to add the numerators or subtract, depending on the problem. And we keep that common denominator. So our denominator is x plus 1 times x plus 2 times x minus 1. The order that you put those factors in doesn't matter at all. And then I'm just going to write my numerator down. Writing it down all together before you start distributing is going to help you avoid things like sign errors. It's really easy to make sign errors on these when you start distributing. So I'm just going to rewrite it. So 2x plus 1 times x minus 1. And then I see that I'm adding a negative, so that's subtraction now. And then x minus 2 times x plus 2. So now we're ready to simplify. So we were focused entirely on the denominator, and now we're going to focus only on the numerator. So we're going to simplify the numerator completely. So we're going to distribute and combine like terms. What if I was like, oh, can I do this? Is that cool?
You have that.
What?
You can't, on the right hand side, you can't subtract it, but you can cancel out x minus 1 on top and bottom, right? Because of the negative.
Why not?
You have the minus.
Because of that subtraction, right? Remember that in order to cancel, the entire numerator and the entire denominator has to be a product. That means no operations other than multiplication outside the parentheses, right? So this is really tempting because of all the parentheses, right? It like looks just like the ones we did yesterday where we canceled, but this subtraction right here means that the entire numerator isn't a product. It's not something times something times something, right? It's something times something minus something times something. So it's subtraction. It's like if we had, if we wrote like 10 twelfths as 2 times 3 minus, no, not 2 times 3. 5 times 3 minus 5 times 1 over 2 times 3 times 2. You can't cancel the 3, right? Like that doesn't make any sense. So we have to write the entire numerator as a product in order to do any canceling. And a good general rule on these problems to remember is that the only canceling you will ever do when you do addition and subtraction problems will be in the very last step. It'll be the last thing you do. So if you find yourself crossing anything out before that, then you're probably doing something that isn't actually like legal. So at this point, we want to distribute. So we have 2x squared minus 2x plus x minus 1. I don't need those. But here I do need the parentheses because we have this negative that we're going to have to distribute. And so when I multiply x minus 2 by x plus 2, I haven't yet distributed the negative that's in front of that whole product, which means I need the parentheses around the product. Otherwise, I never get to distribute that negative. So this ends up being x squared minus 4, right? Because this was a positive 2x and a negative 2x. So my middle term's added to 0. So we have x plus 1 times x plus 2 times x minus 1. And now we'll distribute that negative. So I have 2x squared. I'm going to combine that negative 2x and x here. Minus 1 minus x squared plus 4. And the reason I'm not distributing in the denominator is that the idea of all of this is that we want to simplify any fraction that we get as our answer. And to simplify a fraction, the numerator and denominator have to both be factored. So that's the reason I'm doing everything I'm doing with my numerator, is so that I can factor it. The denominator is already factored, and so there's no reason for me to distribute it all out and then factor it all again. So the denominator is already in the form I want it to be in, which is why I'm not doing anything with it at this point. So my entire focus at this point is on the numerator. So we have 2x squared minus x squared, which is x squared. Then we have negative x, and negative 1 plus 4 is positive 3. X plus 1, x plus 2, and x minus 1. So now we're at the point where we can simplify the fraction, if possible. So we're going to factor the numerator. And cancel common factors. If possible. But don't be alarmed if it's not possible, because remember, just like we said with that numerical example at the beginning, like sometimes you just end up with like something that's big and uglier than maybe you want it to be, but it's perfectly common for that to happen. It doesn't mean that you did something wrong. So in this example, we can't go any further than this, right? Because AC is 3 and B is negative 1. So these would have to both be negative, and the only possibility is negative 1 and negative 3, which definitely don't add to negative 1. So this just, the numerator can't be factored, which means that we can't simplify this fraction any further, so we're just done.
So you just like leave it, you don't have to write anything for it, just leave it as
Yeah, that's the answer. So that's what, that fraction is what we get when we add those other two fractions. Good. So shall we do another one? I'm not gonna lie, like these are kind of tedious. Like they take a lot of writing and a lot of time. But I will tell you, and I promise, I get no joy out of making you do more work than you have to. If you take your time and you write out every single step the first time, it will save you time in the long run, because you won't make little tiny mistakes and then have to do it like 5 more times. I promise. If you just take your time the first time, it'll save you all sorts of misery later on. Okay, so here we go. Let's do how about we'll do this one. X plus 5 over 6x minus 9 minus x plus 2 over 3x plus 3 minus 6x plus 10 over 6x squared minus 12x minus 18. Okay, we're going to start by factoring just our denominators. So we have x plus 5 over, shoot, I miscopied this, I'm sorry. This is 18. Sometimes if I miscopy an example, I can just roll with it, but this, like, these get really, really messy if the denominators don't work out to a really nice LCM, so I have to change it. Yes. Okay. So I can factor a 6 out here, and I have x minus 3. And then I can factor a 3 out here, times x plus 1. And this one's a little more involved. It takes a couple steps, so we'll just write it over here. So I have a GCF of 6. And then this factors into x minus 3 times x plus 1. So we have 6x plus 10. And notice like that theoretically could be factored, but we don't factor any numerators in this step, so we're just leaving it alone. And then over 6 times x minus 3 times x plus 1.
Why don't you factor like a 2 out of the top of that?
Because we don't factor the numerators.
Okay.
Because eventually we're going to be adding and subtracting them, which will require us to distribute again. So we're just focused on the denominators. You can kind of think of it if you look at our steps, like this is all denominator. This is all numerator. And then the last step you cancel if you have anything in common. So you'll never be like working on both at the same time, kind of. So now I want common denominators. So we've got x plus 5 over 6 times x minus 3. Do any of the other fractions have factors in their denominator that I don't already have? The x plus 1, good. Do I need a factor of 3? I don't, because 6 already contains a factor of 3, right? That 6 is like 2 times 3, which means I don't need another factor of 3. So all of these already have a factor of 3 in them. And then minus x plus 2 over 3 times x plus 1. Do any of the other fractions have factors that this one is missing? I need an x minus 3. Anything else?
2.
Yeah, I need a factor of 2 because the other fractions have a factor of 6, which is 3 times 2. You can, it might help if you look at it like this, like if we think of factoring these. Like this is 2 times 3, and this is 2 times 3. Right, so everybody already has a 3, but the first and last one have a factor of 2 that the middle one doesn't have. And then minus. Does this one, do the other fractions have any factors in their denominator that this one doesn't have? No, this one has them all. So that's kind of nice because that means I don't have to multiply by anything. Some people really like to multiply by 1 over 1, and if you like to multiply by 1 over 1, you can write it, but in reality, like, we just don't need anything here. Okay, time for the big guy. So my denominator is going to be 6 times x minus 3 times x plus 1. I'm going to have x plus 5 times x plus 1 minus, and I'm going to put the 2 in the front just because we're sort of more used to seeing it that way. And then minus 6x plus 10. Be really careful that you include your parentheses, right? Because we're going to have to distribute that negative. And if we didn't include the parentheses around the 6x plus 10, that's really easy to miss. Okay, I'm going to hand back papers and let you guys simplify from here, and then I'll show you what it ends up being. But I want to give you guys a chance to try it. Okay, that's better. Yeah? So that middle bit, we multiplied x plus 2 by x minus 3 and got x squared minus x minus 6, and then distributed a negative 2 to it. So that's how we got there. So when you multiply that x plus 2 times x minus 3, you need to put the result in parentheses and then distribute the negative 2. And so this ends up with negative, oh, whoops, I didn't write my denominator. So negative x squared. Then we have 6 plus 2 is 7, minus 6 is negative 1. And then 5 plus 12 is 17, minus 10 is 7.
You just said 6 plus 2 is 7. Is it 8?
Yes, it's 8, thank you. Minus 2x. And that doesn't factor anymore. Like, we can factor out a negative 1, but it still doesn't factor.
Isn't it a positive x?
Yeah, isn't it positive?
Yeah.
Because you got 6
It definitely probably is.
8x minus 6x.
Yes. I'm sorry, I'm rushing because I really want to give you back the rest of your papers before you have to go. Does it look good now?
Yeah.
Okay.